and it is again a special one, as we are delighted to co-host it with our dear family member, the Green Powered Future Mission, which is part of Mission Innovation as well, and which is a key partner when it comes to accelerating electrification in industrial production. Thank you all for joining us from across the globe. And once again, we have a truly international audience. I'm speaking to you today from Vienna, Austria. And whether it's morning, afternoon, or evening where you are, we are really delighted to have you with us. Thank you for being here. It is my pleasure to welcome you on behalf of the Net Zero Industries mission. And let me briefly introduce our mission. And yes, thanks for changing the slides. So in a nutshell, we are a global initiative under Mission Innovation. We are committed to accelerating the transition of energy-intensive industries, including cement, steel, and chemicals, toward net zero carbon emissions. These sectors are fundamental to our economies and together account for roughly a quarter of global greenhouse gas emissions. Transforming them is therefore essential to meet our climate goals. And reducing emissions in these industries is especially challenging due to the complexity and as well due to the high costs that are involved. While many breakthrough technologies already exist, they still need to be scaled and brought to market. And if we could move to the next slide, you see an overview. Yes, so our goal is to implement 50 large-scale demonstration projects across energy-intensive sectors, exploring a wide range of technological pathways. We support the rapid development of breakthrough low-emission technologies, and we would like to help them progress to higher technology readiness levels, while at the same time reducing capital expenditure. And one of the key reasons we host these webinars is to share knowledge, to promote innovative solutions for the net zero transition. Building trust in new technologies begins with understanding, and knowledge is therefore essential. Over the next 2 hours, we will spotlight a particularly important lever for the transition, one that has already gained a lot of traction, but with the potential by far not yet fully tapped. It is electrification. And today we brought together technical experts, researchers, practitioners, decision makers, and industry leaders to explore the potential of fossil fuel use reduction, enhance energy efficiency, and support system flexibility. Let me quickly go through the agenda. So we will have a keynote from Jonathan Moncada Botero. He's a researcher at TNO, and he's representing the IETS TCP for electrification in industry. We will then have Veronika Wilk, who is a senior researcher at AIT, Austrian Institute of Technology, and Doris Hofbauer, who is a project manager at Takeda Manufacturing in Austria. And they will look at the question on how to produce high pressure steam with heat pumps. We will then have a presentation from Daniel Rennie, who is the CEO of LELAC. And his presentation will be about flexible electrification of high temperature industrial heating to support lower cost production and more stable energy grids. There will be a live Q&A, and there will be further presentations, if I'm not mistaken. Yes, exactly. Then we will have a presentation from Emma Mooney, who is lead industry analyst from the International Energy Agency, and her presentation will be about industry in the age of electricity, maximizing the benefits of heat electrification. And then we have 2 more presentations, one from Barbara Del Corno. She is a senior researcher at RSE Italy, and it's about industrial waste heat recovery and the potential and economic feasibility for district heating in Italy. Last but not least, Juha Niemi, sales manager from Polar Night Energy Oil, will shed some light on industrial decarbonization with the sand battery. And I forgot to mention that, of course, Luciano Martini, who is the director of the Green Powered Future Mission, will come right after this brief welcome note to share his welcome note and to present his mission, the Green Powered Future mission. And I see that Alan Monaghan is joining as well. Let us quickly let him join the group. He will be our moderator for today. There has been some technical issues at the beginning. I hope he is able to join us now. Let us quickly check that before I'll hand over to Luciano Martini. Just a second. Let's see if that's working. Alan, can you hear us? Are you with us? Let's try this quickly.
Hopefully we are now working, but please continue and I'll take over after Luciano.
Very good. Okay, great to have you. I can hear you well. I can see you. And by that, Luciano, the floor is yours. Great to have you and great that we are able to co-host this webinar together with the Green Powered Future mission. Please go ahead.
Yeah, thank you, Urban, and good morning or good evening, Alan. Good morning, good afternoon, everyone. I'm Luciano Martini from RSC, and I have a pleasure to be the director of the Green Power Future Mission. So first of all, I would like to thank NIM, Net Zero Industry Mission, for inviting us to co-host this webinar. This was a very nice of you, and I think such an important topic as industry electrification should deserve this joint effort. I would also to congratulate the NIM for successfully hosting the NIM Award at the COP30 UK Pavilion. I was there and I really appreciate all the awardees and the activity. So in a few words, I want to just to introduce you very quickly the Green Power Future Mission. Next slide, please. So we have a very ambitious goal to demonstrate that by 2030, we have a power system around the world able to accommodate up to 100% variable renewable energy. And this need to be applied worldwide in order to have an impact on climate change. And we want to prove that the solutions are already available to make the system running under 100% VRE, but still keeping and maintaining a cost-efficient, secure, and resilient system. Demonstrate is a key word for us, so we want to demonstrate solution in real world, in real asset, and the idea is really not only to cover technical aspect, but also other enabling factors like market design or business models and the regulatory framework. And all of these results from our activity will be made available. We develop what we call GPFM Toolbox, is an open internet-based platform where we are storing all the results or the achievement from our mission. For this activity, we can rely on a very strong coalition. You see here that GPFM is co-led by China, UK, and Italy. We have many members from mission innovation countries. On top of that, we can rely on international organizations and key actors from the private sector. So I would like to say that our mission is really a public-private partnership that is working in good harmony and a very nice cooperative environment. So the mission is organized around three pillars. The first one is led by China, is organized around everything breakthrough in renewables and integration of renewables in the power system. The second pillar is led by Italy, is about system flexibility. You mentioned, Urban, this important aspect, and we also cover market design and other relevant aspects. Power to X, power to hydrogen, electrification of industry is also there. And then the last pillar is led by UK, is everything related to data and digitalization, making our system connected and real-time monitoring. All this stuff is included, including interoperability issues. Next slide, please. So in this case, I want just to recall how important is to leverage synergy and to collaborate with the other mission. In our case, what is important is also seeing the possible mutually interesting topics. We already established a long track record of collaboration with urban transition and clean hydrogen. And now we are very happy to have this first attempt of a joint webinar. I say first because I really hope to have a few more in the near future. And we are starting collaborating with you such an important topic, as I said, as industry electrification, and also with the zero emission shipping. So in future, we also are looking for other possibility for collaboration with the other family in our mission, that the carbon dioxide removal integrated by refinery. I think next slide, I want just to thank you for this and look forward for a very exciting and interesting webinar. Thank you.
Thank you so much, Luciano, and it's good to see you again, my friend. And a big thank you to Urban for stepping in when I had some technical difficulties here. My computer was releasing small amounts of carbon that it should not have been doing. Our keynote speaker is Jonathan Mancado Botero. Jonathan is a researcher in process engineering and techno-economic analysis working in industrial decarbonisation projects. He works at TNO on topics such as solar hydrogen, biomass-based fuels, integrated biorefineries, and system-level modelling for defossilization strategies. His keynote presentation today is called the IETS TCP Task 19, Electrification in Industry, and he's going to be updating us on its current status and ongoing activities. Please welcome Jonathan.
Yeah, I'm sorry. For some reason, I cannot see my screen. Is it being shared? Do you see it?
It hasn't gone to display to presentation mode yet.
Okay. I hope not. No.
That's perfect. Yes.
Okay. Sorry for the small technical issue. Thanks everyone, and thank you for the invitation of presenting the task 19 of electrification of industry. I will give a brief overview of the activities that we have been doing in this task. But first, I would like to have a few words about the IETS TCP, that stands for Industrial Energy Related Technologies and Systems. It's a TCP that was founded in 2005. It focuses on energy across many sectors, from processes to whole systems. It really looks at systems analysis, energy efficiency, and look for low cost and savings, especially towards reduction of greenhouse gas emissions in industry. And the mission of it is to strengthen international collaboration to accelerate the research deployment. Currently, there are several members like Austria, Canada, Denmark, France, Germany, Italy, the Netherlands, Norway, Portugal, Sweden, and more recently, Switzerland and the UK have joined. And there are several sponsor organizations from countries that are participating in different tasks, like the case for Japan, Ireland, Finland, Spain, and more recently, Belgium and Colombia. So there are 9 tasks ongoing at the moment. There are varying from more technology-specific tasks, like for instance the membrane processes in biorefineries, to more system-level tasks, like for instance the one on electrification of industry that I will be speaking today, and those like for instance of process and system integration for electrification for industrial decarbonization. I would like to highlight why to join the IETS TCP, mostly because it offers the opportunity to network the work of different research groups, to have access to this work, and also to expand knowledge and exchange knowledge from different countries and initiatives on specific topics. And the main contribution from participants is on bringing the projects to these network activities, participate actively in these activities, and possibly contributing into the workshops and publications from the different tasks. So now I will move into why this task started. So as you know, there is the need to decarbonize and defossilize the industrial sector, and we hope to have an ideal world that everything works fine. So in that case, I just wanted to make an analogy with the ideal equation of a state, those that are fans of thermodynamics. And we hope that in that specific setting, ideal world that we have available green electricity that is actually cheap and that industry is hardly affected by any change. And if we have all these things together, then it will be a piece of cake just to electrify industry. But we all know that that is not the case. Then we have this guy that starts to think, okay, but what will happen if we don't have the ideal representation of the equation of a state? And there are questions that start to appear like, but green electricity is intermittent. There is not enough installed capacity. There is grid congestion, for instance. Do we focus on direct electrification, or should also be electrification of feedstock through hydrogen? How do we deal with intermittency? How do we store energy? How big it should be to cope with the system pressure? And many industrial operations are not flexible. How do we rethink how industry is designed? Do we need to shift it? How do we need to make those changes to make to commercial operation process? Will society accept it? How do we develop the necessary infrastructure, for example? What are the negative or the impacts of electrifying? Will that deplete scarce resources, like for instance, water or metals? And then it becomes a very difficult maze to dig around, and then this guy gets a bit confused. But because of all these questions, then we started to think, I mean, it's very important to have an international platform in which we can exchange information and different angles on trying to solve these questions from experiences from different countries. So this task has been ongoing for several years now, and there has been like consecutive subtasks. Subtask number 1 was initial attempt to map the activities where was the main workforce on electrification happening, and from that a multi-year plan was built for subtask number 2 that finished a couple of years ago already. And in subtask 2 we were looking at aspects like, for instance, the role of process integration and flexibility, understanding topics on technology development and the barriers for technology development, but also systems analysis projects. And now we are in subtask number 3, in which we look at different aspects that I will mention in a moment, but deep diving a bit further and giving continuation to subtask number 2. Among the participating countries that we have in subtask number 3, we have most of the countries that are within the IETS membership, but we also got the opportunity to involve Belgium and Belgium, Finland, and Colombia that are not part of the IETS countries, but more as a sponsor. So the thematic areas that are covered in subtask number 3 involves like to have an overview what is the current status of electrification installations in the different countries and what are the main domains for those applications. That is more a desk work, like to have an overview. Like for instance, in the Netherlands, there has been like a survey and a detailed breakdown of what projects are being subsidized by government, for example. We also are deep diving more into case studies on technology development and technology implementation. Also case studies on systems analysis and systems impacts. We will have a look into the role of process integration and energy intermittency and what does that mean for electrification. And last but not least is how electrification how it stands compares to other defossilization measures, like for instance, carbon capture and storage or biorefineries, and how they complement each other. So we also aim to have a merit order for electrification of industry in this subtask. So far we have started in subtask number 3 the engagement of participants. We have had a kickoff meeting. We've been in the phase of collecting the projects and making an inventory of the participating parties in the task. We have already had our first workshop, and it was on technology development and implementation. And we have received kind number of projects. So we have received approximately 14 projects on systems analysis and system impacts, 8 projects on technology development. So far, 1 project on current status of electrification installations, 3 projects on electrifications versus other defossilization measures, and 4 projects on the role of process integration and intermittency. So this is already a very good outlook of the number of projects that can be networked and shared within our task. So we have had our first, and I'm about to finalize my presentation, is on the workshop of technology development and technology implementation, where we had like breakout rooms discussions, but these discussions came very fruitfully to highlight main key points. The questions that we pose is what were the main barriers for implementing electrification technologies, and what are the main challenges. And basically, the first key message is about economics and policies set the pace, so that translated that the high upfront cost and volatile energy prices really is slow investment, and of course the climate policy will be very important to support the schemes to enable projects. The energy and other aspects that really came across is like the energy network infrastructure are hard limits in the system. The limited grid capacity and the low reinforcement, and in some cases even spatial constraints in already industrial settings are really bottlenecks for electrifications, even if business cases seem positive. Also, the risk perception and company culture are strong barriers. Many companies, they said, we don't want to mess up with our already running plant. This mindset also, and this cautious mindset also prevents a lot on moving forward. And as a main message as well, that collaboration is the main accelerator. Earlier and a stronger cooperation between industry, technology suppliers, and grid operators, policymakers might enforce a faster deployment of electrification technologies. So with this, I am closing my presentation, and thank you for your time. If you are interested on participating in the task or any potential network activity, feel free to contact me and we can have a talk about it. Thanks a lot.
Excellent. Thank you, Jonathan. We are running today's webinar slightly differently to previous ones in that we're going to have 3 speakers speaking before we come back to questions and answers. So I have a couple of questions that I'd like to ask Jonathan, but I'm going to hold them off. In the meantime, everyone, if you'd like to put your questions in the chat or in the Q&A, we'll be able to come back to those after our 3rd speaker, and then we'll be doing another session for the second 3 speakers at the end of the webinar. So with that, get those questions ready. But now I would like to introduce our second speaker, or second and third speaker of tonight. Together we have 2 presenters. We have Doris Hofbauer and Veronica Wilk. Doris is the project manager at Takeda Manufacturing Austria, and she specializes in refrigeration and heat pump technology, whereas Veronica Wilk is the thematic coordinator at the Austrian Institute of Technology, focusing on decarbonisation of industrial processes. Together, they're going to be presenting about the AHEAD, or AHEAD, Advanced Heat Pump Demonstrator, and how to produce high-pressure steam with heat pumps. So if I can introduce you both, Doris first, I believe, or Veronica, over to you.
Thank you, and hello, everyone. Veronica and I are very delighted to present our AHEAD project to you, to show you one way to produce steam with high temperature and high pressure for a production site with a heat pump. The project consists of 2 parts, shown on the next slide. Firstly, there was the research part where we looked if it's possible to install and provide a heat pump system with enough energy and with enough waste heat to operate perfectly in our system, and to provide enough steam at the right pressure level for our production site. On the second side, we looked to implement this system because on the first side we demonstrated and we modeled the system, and then we installed it and tried to build it to verify the data. On the next slide, you will see in 2019 we built a centralized chilled water system on one of our sites with the refrigerant ammonia. This was installed on the biggest site in Vienna for the Takeda Manufacturing AG. And we tried to build it as centralized as possible for this site. We built 3 chillers with 2 megawatts chilled water, and we covered one of the chillers with a heat pump to provide our heating system with 70-degree hot water, so that we can provide the heating for the whole site in winter. We also looked at the data, because we have a monitoring system, and we saw that we need 4 megawatts of chilled water in the summer and approximately 800 kilowatts of chilled water in winter. So we scaled the heat pump that it's possible to provide heat in the winter and use as much heat in the summer as possible for our heating system. The head system is connected after the first heat pump. On the next slide, you see the head system a little bit closer. So you can see the 70-degree water enters the steam heat pump, where we generate steam at 120 Celsius temperature and 1.9 bar absolute. This system is built or manufactured and developed by SPH. It's a manufacturer in Germany. The size of the head system is 1.7 megawatts. It's the maximum heat that we get from the first heat pump, so that was one of our regulatories. And we tested the system at the manufacturer site and measured a COP of 4.4, which is very good. It's also provided with butane, so we have a cascade system, and it only uses natural refrigerants. The second part is the steam compressor, which is provided by spilling, and which lifts the steam pressure and the steam temperature up to 184 degrees and 11 bar absolute pressure. The system then feeds into our production site and provides around about 2.5 tons of steam per hour into our network, and that's just from wasted heat because we use heat pumps for the whole system. Veronica will now tell you more about the modeling and the scalability of the developed system.
Thank you very much. And I would like to share these 2 diagrams with you that give you more insight into how the boundary conditions of the head systems look like. So as we have heard before, there's already a chiller in place and the heat pump for space heating. And the blue line in the diagram shows the amount of waste heat that is available from the chiller. This is data from the year 2022, and we see here that lots of waste heat is available in summer because there the cooling need is the highest. The red line shows the space heating demand, again, over the course of 1 year, with the high demand in winter and lower demand in summer. And this is how the source for the head system looks like. On the right, we have the steam demand, the black line. The steam demand varies with the needs of the production and ranges from 1.5 tons per hour up to 2.5 tons per hour. And there's also some seasonal variation in there. And the first question in the research project was how to design the head system, how to select suitable components, and how to size it properly to provide the maximum amount of steam that is possible, so that we can contribute a lot to the CO2 savings on site. So it was about the number of compressors, the steam generating heat pump, and also the number of compressors that are used for steam compression. And another important question was the temperature in between these 2 heat pump systems. So how high should the temperature be that the steam generating heat pump is producing, and where should the steam compressor then take over? And to solve this question, we have carried out a large number of annual simulations, basically simulating 162 versions of this system to come up with the best suitable compromise between investment and operation costs to yield as much steam as possible, also considering economic boundary conditions. And the layout that came out of these simulations, this was the one that we've just seen before. The project is now in a very exciting phase. So we had the official commissioning of the system in September 2025, and now we are in the operation phase, and the project goes on for another year. And this allows us to scientifically monitor and optimize the system for about 4,000 hours. The aim is to show that the system is capable of considerably reducing the CO2 emissions on site. So we aim for about 80%. This was also a result of the simulations. And the system will also allow the production site to use almost CO2-free steam that is produced for more than 7 months a year. And we will have a closer look on that. That's also a result from the annual simulations. You see here the steam coverage that is provided by the AHEAD system. And from April to October, those are the 7 months where we can almost completely cover the steam demand with the heat pump system. As the temperatures decrease in October, November, December, the space heating demand is more dominant, and there's not enough heat source available to operate the AHEAD system. So it goes out of operation and will restart in February or March, depending on the outside conditions. And with the monitoring, we will also verify if the year 2026 look like the case that we see here, which is based on the data from 2022. And as an outlook, I also want to speak a little bit on the multiplication potential of this system. So at the Takeda site, the heat pumps are integrated on the supply side. So the heat pumps are used to supply cold and steam. And this is transferable to many other sectors, for example, to the chemical industry or the paper industry. And in this illustration, I also would like to show you on how to decarbonize a very general steam production system. Here you see the traditional approach, a gas boiler that produces high pressure steam, for example, at 10, 15, or 20 bar. And then depending on the specific needs of the process, the pressure and the temperatures are reduced with expansion valves to feed the different processes. If we do this with a heat pump system, we have to flip the perspective upside down. We start with the heat source with a closed loop heat pump that produces hot water, and another heat pump that then produces steam in the condenser, very similar to the system that we have implemented at Takeda. And for the remaining consumers that need higher pressures, we then add steam compressors to come up with all the temperature and heat demand within the process. And in the end, we can then switch off the gas boiler and run the complete system on renewable electricity. When implementing those systems, it's important to think about the actual needs of the process. So what temperatures are really needed, not necessarily maintaining the temperature level of the supply as it was in the past. Integration is really crucial for the efficiency of the solution because the electricity consumption of a heat pump really depends on the temperature lift, on the temperature difference between the heat source and the heat sink. And the lower the temperatures are, the more efficient the process will become. And yeah, that's already our last slide. Within the AHEAD project, we demonstrate that it's possible to produce steam with heat pumps at 11 bar and 184 degrees C. This is a result that we've already achieved. The system is integrated at industrial scale. It's the first of its kind that is operating at a pharmaceutical site supplying steam. And with this project, we like to contribute also to the diffusion of heat pumps in industry, because they are a very interesting option for process heat supply. They allow for reduction of CO2 emissions. We can recover the waste heat that's already available on site. And we believe that demonstration projects like this are very important to establish new technologies and to showcase new options for process heat supply. Thank you.
Excellent. Thank you both for that presentation. It never fails to amaze me how prolific steam is in every process in almost every industry around the world. Again, remember, please put your questions in the chat, and after our next speaker, we'll be coming back and asking questions to all three of the first presentation groups. Next, I've got the pleasure of introducing Daniel Rennie. Daniel is the CEO of Lilac. His background is in the electricity industry. He helped set up the European branch of the global CCS Institute. He ran the European Commission CCS network, and then he joined Calix in 2014 to investigate its technology application to cement, eventually becoming the CEO of Lilac as it was created in 2021. Please join me in welcoming Daniel. His presentation is going to be titled Flexible Electrification of High Temperature Industrial Heating to Support Lower Cost Production and More Stable Energy Grids. Daniel, over to you.
Right. Well, thank you very much, and thank you for inviting me to this really interesting conference. And again, I hope this intervention joins into it because Lilac is really about capturing the unavoidable carbon emissions from the cement industry. It's a carbon capture approach, but we've really been finding the electrification and some of the side benefits of electrification of this industry really having some quite wider impacts. So in terms of just how the cement industry fundamentally works, the main ingredient is limestone when making cement. And the reason it's a hard to abate industry is because it loses almost half of its weight when it's processed. So on the left, there's a simple diagram of basically what's going on at the cement plant. There's a heating source, normally fossil fuels, and that gets used to drive the CO2 off the limestone. And those combustion gases and CO2 gets mixed. That comes out of the chimney at the top. And then the calcined meal, the decarbonised meal, continues its journey on through the cement making process. This is where all of the process emissions effectively get separated. The Lilac approach is a little bit different in that it just keeps those unavoidable process emissions separated from the heating source. So we do have a furnace, and on the inside of those furnaces, we have steel tubes, and they're completely contained. There's nothing in them apart from the material being processed itself. So very simply, we drop material down, the limestone. It goes down these heated tubes. The furnace heats them up to over 1,000 degrees Celsius. As they get heated, they release their CO2, and we get a very high purity CO2 coming out of the top, and just the normal decarbonised product down at the bottom. So the idea about this is that we capture these unavoidable process CO2 emissions at very cheaply, and it's cheap because we don't need additional energy or very little additional energy to separate the CO2. And then it also gives us flexibility about the heating source that is used. So about 90% of global cement plants use coal still. This big drive towards alternative fuel, but this also allows the electrification of this process, again, because we just need to heat these steel tubes up. So we did receive some EU money, and in 2019 we built this pilot plant called the Lilac 1 pilot. This is in Belgium, and you're very welcome to come visit it if you wish at Heidelberg Materials plant in Lix. And this was built to prove that the process works. So it has one of these commercial size full-scale tubes in it, and it's showing that we do get a very pure stream of CO2 coming out of the top. It's also showing that we don't need chemical solvents or any other additional materials or input streams to separate that CO2. And it's really proving the basis of this technology. And again, it's just taking a slipstream of its normal cement meal or limestone, processing it through it, and it just continues its journey through the normal cement making process. Because we just need to heat steel up, again, we can use different fuels. We're looking to use waste fuels, these alternative fuels, which are often quite high biogenic content. And all of that means that for capturing these process emissions, Lilac, this indirect calcination approach, really can be quite a low-cost way of capturing CO2 from the cement industry. And that's really important because cement is something that we all need. It really needs to be a commodity product that's produced as cheaply as possible. That's really why it's it is a difficult to abate industry. And again, keeping costs down is very, very important. Now, as I mentioned, we can electrify this process, and we've built a number of different plants proving the electrification. We can get to the temperatures required without any difficulty. But one of the interesting things about applying this to the cement industry is that the average electricity price is just too expensive, fundamentally, particularly compared to, fortunately, fossil fuels and these other fuels. Electricity is a really good energy source, and it is quite expensive. One of the approaches that we've been developing, particularly over the past few months, is a different way of electrifying it, where we effectively use these steel tubes as the resistive element, so allowing direct electrification of this process. And that means that we can also switch between fuels. We can still have the furnace using a conventional fuel or alternative fuel or biomass, and then we can switch between that and electricity to varying degrees very quickly, really within minutes. And so suddenly this is a way of allowing the electrification of industry by using just electricity when it is cheap, or certainly cheaper than the fuel that it would otherwise be using. And so this is a way of enabling deployment, we hope, in the short term, capturing these unavoidable emissions and introducing the electrification of industry. And again, as more electricity gets deployed more cheaply, it does allow, it's effectively ready to be fully electrified. But it does show that we can actually get cost savings for just normal cement production through this use by being able to use these electrons when they're cheaper. So on one hand, we've been looking at it from our client's perspective, keeping cement production as cheaply as possible. But there's also a benefit to the grid. So there are batteries, of course, we've been, and industrial plants can turn down their electricity demand. But there's very little that we're aware of that can turn up demand on a seasonal or very quickly basis when the grid demands it. So batteries typically operate on a daily basis. This is really saying, well, actually for a given number of days per year, we could withdraw electricity when the grid demands it. So this is a way of we think complementing the toolkits that TSOs, grid operators, need to enable stabilization and more renewables to be deployed. And for context, a full-scale cement plant operating one of these plants would be withdrawing potentially up to 100 megawatts of power, again, very flexibly when the grid demands. So again, we think this is quite an innovative way of allowing electrification, provide grid stability, and actually reducing production costs while capturing this unavoidable emissions. So we really are looking for the synergies that can be made. So the Lilac 1 plant has been built in Belgium. It was built in 2019. Again, that's got a single tube. We build by effectively a modular basis. We just have more of them. We're currently investigating multiple sites, effectively capturing around 100,000 tons of CO2. And I suppose on an electrical basis, it'd be about 25 to 30 megawatts of draw. And those can be duplicated to get to any size of cement plant. And again, we're working with companies across the world. So again, we really do think there are these options for decarbonisation at lowering production costs, combined with enabling further rollout of renewable sources. And again, really do wish to collaborate with yourselves and more broadly to really ensure that we can modernise industry in a really exciting and completely mutually beneficial way for all of the stakeholders involved. So again, I think Alan, you've popped up. So thank you very much for your time. And I think we're almost at the point of taking questions, but over to you.
You had a minute left on the clock if you wanted to make any other points.
talk forever on this.
Well, I'll give you some questions in a minute, but I will, just for continuity, jump back to our first speaker for our first question. I've got a few that have come in. If I could, to Jonathan, which part of the system needs to change first to make industrial electrification feasible? Is it the technology? Is it the infrastructure? Or is it policy?
Well, that's a very interesting question. But I think from our perspective, I think it's a combination of the three. But it is clear that without the right policy incentives and the right policy mechanisms, the change is more difficult. So there should be the right incentives because technologies are moving a bit faster, but policy is not there yet. And that also delays a lot technology implementation and also infrastructure expansion. So I think it's a bit of both. It's a bit of everything.
Unfortunately, it seems to be that for almost everything we discuss in technology fronts, it's usually a combination of factors that makes it so much harder and a barrier for those hoping to help. A follow-on question though for that then is, so what do you see as the biggest practical challenge for electrifying industrial processes today then?
I think one, well, at least from what we have discussed in the task, I think one of it's really the flexibility issue, and the main, I think practically, is what does that mean for current industry? So will that be that buffering, where buffering is happening, and sometimes we are pinpointing or we're playing ping pong, that not pinpointing, playing ping pong industry and other sectors of society, like where does buffering needs to happen, but buffering is indeed a very important aspect. But sometimes from an industrial perspective, we tend to push that buffering needs to happen outside the industry gate. But in some other cases, well, like the power sector says, but maybe industry could be as a battery for dispatching electricity as well. So it's difficult to say. But in my opinion, I think this is one of the biggest barriers, how to deal with the intermittency and the flexibility of the new industrial settings in general.
Excellent. Excellent. Thank you for that. A question that's come in for Doris, if you'd like to put your camera back on, and there'll be a question for Veronica right after it, I can see. So for Doris, you mentioned 7 months of operations. Are there other heat sources available for Takeda to actually operate the system during winter?
At the moment, we have the existing gas boilers for backup, so they will operate if the AHEAD system is out of operation. But we look into other solutions to use existing waste heat to provide other heat pumps to close this gap.
Excellent. Okay, thank you. And whether this is a question for you or for Veronica, I'll let you choose. You mentioned the temperature of 184 degrees during the presentation, but is that the highest temperature that can actually be achieved with the AHEAD system?
It's the highest temperature that Takeda needs on their site. So this was the design goal, but with a very similar setup, the combination of the steam generating heat pump and the steam compressor, we can also go to higher temperatures by adding another stage of steam compression. So to go beyond the 200 degrees as well. But this really depends then on the need of the process. And when we talk about these high temperatures, I would always like to add, please think if you really need those temperatures, because it's really an effort to go there.
In fact, that's one of the themes of the Net Zero Industries mission, to actually look at efficiency. Many times we've taken things for granted. We do what's available or what's easy, but if it's a waste of energy, it's a waste of energy. So excellent point. A question, if I could then, I've spread them around, for Daniel on Lilac. You showed in your graph the lowest cost of capture for Lilac relative to the other technologies. But is that because you're already accounting for the benefits of low-cost electricity or those grid servicing revenues that might come in?
No, actually, that graph, that really was just through the application of the technology without electrification. That really was just the ability to use these fuels and separate CO2 at capturing this unavoidable process emissions. So as has been brought up, it is really difficult to make these steps within industry about these transformations. And it's really been the last few months that we've been investigating this electrification or hybrid operations and getting these additional benefits to cement making processes. So actually there's got the potential to reduce their normal operating costs further, which is exciting. So again, seeing these benefits is good. So in answer to your question, no, that was just normal CO2 capture from our point of view, with the electrification having additional benefits.
And it's good to know there's more on offer. A question, this one's from me actually, because I have a very big interest in grid balancing and load balancing. Grid balancing is actually something that's already done in other industrial facilities. So what is different about the LILAC system?
Yes, so normally a grid always needs to meet demand. Otherwise, we get blackouts, as we've seen over the Iberian Peninsula. You're quite right. Industrial sites normally can turn down their production. So that's normally what they'll do. They'll get a call from the grid saying, can you stop using your mill or stop producing altogether on a certain day? And that's a way of reducing demand. Batteries are, I suppose, a little bit different. They will they will increase demand and then resell it. So that helps balance prices. But normally industrial sites can only reduce their demand. What this is doing is saying, well, we don't need to use electricity at all, but if the grid needs it, we can withdraw hundreds of megawatts of power from the grid. And so it's a little bit different. And again, that's not something that other industrial sites do. They're always designed for an electricity draw, not the opposite, creating an artificial one. And it's just a really interesting, we think, we've received feedback from the grid that this is really interesting as just another tool that they can use to avoid catastrophic failures, as we've seen. And that's going to happen more frequently with data centers too, which is changing the demand profile, particularly if they switch over to their own internal generators. So it's going to get more important, we think, as a requirement for the grid.
Excellent. Thank you for that. Now, some other questions that I'm reading off from other people there. This one's a long one, so I'm going to shorten it down, but it's from Brendan. It talks about the efficiencies. It's for the AHEAD team, so for Veronica and for Doris. It talks about the efficiency gains are clear and the emissions reductions are important. But what they want to know specifically is, has there been any economic modelling been applied to look at the CapEx, OpEx and the expected duration of the return of investment from the technology program?
This can be answered with yes and no. So it depends where you want to build the system. We did the research for us. So we looked into the OpEx costs. If we looked what we want to compare with each other. So it's you get another outcome if you use normal gas or you use biogas. For the OpEx cost tracking, and you also get another outcome if you mix both of them. You can use just electricity and no gas, and that's the main point. You have to choose one system to compare. And internally at Takeda, we said, okay, we look into all options, and even if you use electricity, you have a better ROE because you have a COP for the whole system with round about 2.2. So you get 2.2 kilowatts out of 1 kilowatt electricity, and that's better than 1-to-1.
Excellent, thank you. Now, another question's come in for Daniel, and that's, do you intend to use your LILAC solutions to replace a clinker preheater and calciner?
Yes, great question. And it is just a pretty preheater calciner. So we are designing these to be retrofitted. Again, most of these cement plants are quite old and they will continue to run for as long as they can. It would be built alongside the existing preheater, pre-calciner. During the winter shut, that's when the tines would be made, and then that can be largely transitioned over and use as much of the existing asset as possible. But yes, it is effectively a preheater.
Excellent. Now, this is a question that I already know the answer to, but I'm going to ask it because the audience may not. Have you, and it's again for you, Daniel, have you looked into using hydrogen as a heating source instead of electricity?
We have, and in fact, that plant that was built in Belgium could use hydrogen today if it was available. So yes, it's a wonderful energy source. We'd love to use it, and when there is surplus, cement industry and lime industry and direct air capture companies will be in a position to use it. We are ready to use hydrogen, and again, we were talking about efficiencies too. The efficiency when we're using hydrogen and electricity is a lot higher than conventional fossil fuels as well. So they are slightly more expensive at the moment, but again, yes, would be lovely to use hydrogen and electricity.
Excellent. So this will be the last question of this questionnaire, and I'll ask it to Jonathan if I could. And it's a question from the chair, and it's how can people on this call actually be involved in the IETS TCP program?
Yeah, that's an interesting question and very important one. Well, the subtask number 3 is running already, but if your organization is part of the already TCP members, it can be easily included. In the case it is not from any of these countries, the procedure is to go through a sponsorship. I think it's something around $2,500 per year for participating in all the tasks. It is possible as well. But I think the first step could be to contact me, and then I can guide the discussion or lead to who to contact to be able to participate. But the participation is rather simple. I mean, the inclusion is rather quick, so that is always possible, and we are welcoming more participants if anyone is interested. Yeah.
Excellent. Thank you. Well, that concludes the first Q&A, but it also gives me the opportunity to jump straight away to our 4th presentation of this session. It's my pleasure to introduce you to Emma Mooney. Emma is the lead industry energy analyst at the Office for Energy Efficiency and Inclusive Transition of the International Energy Agency, or as we know it, the IEA. Emma has over 20 years' experience in sustainable energy management and has worked in the private, public and research sectors. The presentation that she's giving today is Industry in the Age of Electricity, Maximising the Benefits of Heat Electrification. Over to you, please, Emma.
Good morning, everyone, and thanks. Good afternoon as well, depending on where you are. And thanks very much for the opportunity to be able to present at this fascinating workshop. So I'm going to talk about industry in the age of electrification and how we can maximise the benefits of heat electrification. And I think one of the things is I've been teed up very nicely by the IETS work on process integration, by AIT talking about their case study and how important it is to look at the heat demand first before you size your unit. And that's kind of, spoiler alert, that's where I'm going to be taking this, is about the importance of looking at efficiency first and how we can significantly amplify the benefits of electrification when we do look at the end use first. Move my slide forward. There we go. So first of all, just to look at the potential of electrification. And we did a study some time back, not too long ago, on the potential energy savings from electrification of industry in the United States. And you can see that across all sectors, there's a potential for energy efficiency saving through electrification. On top of the energy saving, it also means that we cut out the fossil fuel demand that we're using, or we can boost process efficiency. We can allow the remaining demand to be met with the low carbon electricity, and we can create new business models. As well as that, I think it's important to say that this is looking at electrification of all processes, but heat globally makes up 2/3 of industrial energy demand and makes up 1/5 of total global energy demand. When we look then kind of at the level of potential for rapid electrification, so what can be done very quickly, we did a study on the electrification potential in Europe. And this is where we focused on what technologies were already widely available and how we could switch to them fairly easily. So what could we do that was easy to abate the sectors that we could move to easily? And you can see there that there's a lot of potential in the already electrified is the light blue, and the dark blue is the rapid electrification. So things that can be done quickly with the technologies that we already have. In light industry, this is much easier because it does take things to switching from fossil fuels to electrifying process heat pumps, microwaves, reverse osmosis or separation. And then in heavy industry, it is a little bit more difficult, as we've discussed, and that it often requires replacing a core process technology. As a result of this electrification, though, we know that the electricity demand would increase, and there would be more pressure on the grid structure and grid infrastructure. So when we look at looking at that infrastructure and where we are, we can look at three things. We can look at the demand side, the generation, and the grids. In the generation side, the construction times for power plants have a huge impact on the total costs, and delays can in a new plant can lead to overruns. But you can see there that nuclear is the one that takes the longest amount of time, with shorter times for the fossil fuel and low emission technologies that can be built much quicker. On the transmission side, you can see as well that the extra high voltage transmission lines, they can take beyond 10 years to be developed. However, when you look at the demand side, you can see that there's a very short timeline in implementing the demand side efficiency, whether this is industrial processes, building retrofit, or EV infrastructure. There's a short turnaround, and they can be easily implemented. The other thing with these is that if we do increase this efficiency, obviously we're potentially freeing up electricity for further electrification. So with that in mind, in the industrial sector, one of the things that we get asked a lot is, or we get told a lot is, we've done all the efficiency stuff, all the low-hanging fruit is gone, there's nowhere else to go. We did some analysis for our competitiveness work that we did earlier this year of about 10,000 facilities in the US, where we looked at, across the same sectors, where we looked at how energy varies for the same product or similar products. And what we saw was that there was huge variation, up to 3 times, between the top 25% and the bottom 25% in industries. And while we know some of this variation is due to differences in the products, it does highlight that there is a potential for many firms to still reduce their energy expenditure and energy efficiency. The analysis that we carried out was that if all IEA countries matched the energy consumption of the best performers in their subsectors, that energy costs could be reduced by about 600 billion per annum. And just to caveat on that, the best performers doesn't mean it's the best performance that's achievable either. So it means there is still potential. Just to put it into a diagram, I wanted to kind of take a look so we could see how much energy is wasted. This again is based on the MEX database from the US, and I just took a screenshot of one of their Sankey diagrams. But you can see across all manufacturing in the US, only 60% of the energy input to the process ends up being used. And in process heating, it's only 67% is used. Machine drives for this, it's only 39% is actually used as an end use. So there's a lot of efficiency there to be made there. When we look in more particularly at the industrial sector, at the food and beverage industry, we can see that there's even more savings to be made. And here, only 48% of the energy input is in applied energy. So there's a lot of saving to be made there. For process heating side, that's around 45% for the process heating side in particular. So by addressing energy efficiency, we get the energy savings, but we also have other benefits that we can have. If we do the energy efficiency first, we can avoid the energy losses and the associated emissions. We can reduce excessive heat loads, so we don't have those excessive heat loads that we were talking about earlier, and the temperature requirements. We can stop designing and investing in large and oversized equipment and technology, although I know that when I worked in this area, I was told that no one ever got fired for oversizing. So we have a job of work to do there in changing people's attitude towards that. We can avoid higher electrical loads and higher peak loads, and we can reduce the high costs that we have for connecting to the grid. Just looking at one of the areas where we think there's a lot of work that can be done, we've done some work on energy management systems and energy management in particular. So when we talk about energy management, we're not just talking about the system, we're talking about the proactive and systematic monitoring, control and optimization. So this includes actually doing the actions that make the energy savings. We analysed about, it says 240 there, but actually we've analysed about 300 industrial facilities that implemented ISO 50001, and we found an average that they got a saving of about 11% in the first few years. But we found that we're finding more and more companies are achieving levels up to about 30% and even higher. One of the interesting things is that when companies have an energy management system in place, then we can see that they get continuous levels of savings. So the energy management system helps them to maintain and continue the savings. And that those savings continue for up to 12 years. So there's a lot of savings that can be made there. In particular, if we apply this to, we're trying to maximize the benefits of heat electrification, we looked this year at the non-electric process heat demand. So this is just process heat demand, and it is in the less intensive manufacturing sectors. And what we looked at is how we could replace the heat there with our heat pumps. And we found that when it was feasible, we could reduce down by about 75%. So we go from about 3.3 exajoules of process heat down to about 0.825, which is a lot. But actually, if we implemented energy efficiency first, we got a 44% reduction in demand across the process heat demand sector. So obviously, leading first with energy efficiency is a key way to move there. Sorry. Again, the benefits of efficiency first, you get increased visibility, control and flexibility on your new system, So when you're doing it with a new system, that control is built in there. There can be increased productivity and production capacity, which leads to competitiveness. There can be reduced operational and maintenance costs. That is for the new system that's being installed, but also for the existing systems. There can be an increase in health and safety and increased compliance with environmental regulations. So we have a lot of work done on the multiple benefits, and we would like to engage more on this because it's a really important part for industry and for adoption. Some examples of measures, there's process integration, which can have huge impact, maintaining and controlling process heat reduction, improving the efficiency of motorized systems is a big one. Energy management, as I said, and the scaling up of AI reductions as well. If we use AI, we've done an analysis recently, and if we use AI in conjunction with energy management systems, we can get an 8% saving, additional saving in our energy use. And this has a payback time of about 6 months. So AI has a huge impact, or can have a huge impact in energy in the energy use of our industrial facilities. Finally, I'd like to highlight just 2 case studies of countries who are doing efficiency first really, really well. And there are many more, as we just saw in the Austrian case. There's the Energy Efficiency Accelerator from New Zealand, where they put efficiency first and work with renewable energy integration and efficiency. And there's the Exceed program in Ireland, SEA Ireland, where they are also putting efficiency first. And in one case, they have a brewing facility that uses 1/3 of the energy of a traditional brewing facility. And with that, I have some IEA resources that we can share, and I will hand back over to Alan now. Thanks very much.
Thank you so much for that. I'm still fighting some technical difficulties here, but I believe I'm now back on live. Again, we're saving the questions until our next block of Q&A at the end. So it's my pleasure now to say thank you to you, Emma, but to introduce next Ada Barbara Del Corno. Ada graduated in physics with top honours from the University of Milan in 1990. My generation. Ada has been involved in the PASM and magnitude projects in Europe and has served on the executive committee for the IEA DHC. The presentation today given is going to be called Industrial Waste Heat Recovery, Potential and Economic Feasibility for the District Heating in Italy. Ada, please, over to you.
Okay, sorry. Okay, my name is Ada. I work in RSC, that is an Italian research center. About my presentation, my presentation is about the potential and economic feasibility for industrial waste heat recovery for district heating in Italy. And in relation to the efforts towards industrial decarbonization and about the four main pillars, we are interested especially in energy efficiency for industrial sector. That means energy management, that means digitalization, but we are interested especially in waste heat recovery. So in RSC, we have developed a web tool for the promotion of industrial waste heat recovery with district heating. It was realized in collaboration with the Polytechnic of Milan. This atlas is based on matching between heat demand and industrial waste heat sources. Using an optimization algorithm, the tool identifies zones where district heating is economically more attractive than individual solution. Another interesting feature of this that atlas is that the user can configure their own parameters as the amount of waste heat, as the cost of energy, and they can apply the matching algorithm to these parameters. So we have three kinds of maps. The first map is about industrial waste heat sources, where it is estimated the quantity of waste heat at different temperature, three different range of temperature. The other map is heat demand for the Italian census zone. And at the end, the product of matching these first two maps is potential waste heat recovery for district heating. The algorithm calculates for each industrial plant how much heat can be supplied through district heating at a lower cost than individual gas boiler. In the map is reported the levelized cost of energy that is calculated dividing the total life cost of waste heat recovering, total, that means cost of CAPEX, OPEX of the technologies, and even the cost and the CAPEX and OPEX of district heating network. And all of these costs will be divided by the total lifetime energy output to obtain the levelized cost of it. Now I briefly show the methodology that we have used for these maps. About it, demand maps, we have considered residential and tertiary sector needs. So for residential, we have considered weather data, space heating demand for square meter, and these coefficients depend on the type of building, single or multifamily, and even the construction year. This parameter will be, it was multiplied by the surface, the building surface area by census zone. So we use the data from ISTAT, that is an Italian Institute of Statistics. Even for tertiary sector, we consider space heat demand per square meters, multiplied by the surface per worker, and multiplied by the number of workers. But because this is the only parameter that it's possible to have by ISTAT for every census area. So we at the end we have obtain a map, demand map for scenario 2030. So we have even considered the refurbishment of the buildings. This is a zoom of the map. This is the census area. And the dark blue is the census area where the heat demand is higher. About the industrial waste heat map, we have considered the companies that are registered in emission trading system register. So using the CO2 emission divided by emission factor, we obtain primary energy, and this primary energy multiplied by the waste heat coefficient, we obtain the quantity of waste heat that we estimated. This parameter is theoretical. We obtain this parameter by reference. This parameter depends on the industrial process. So we have a different parameter for iron and steel, for paper mill, and so on. And it is different for 3 different level of temperature. We have high temperature, more than 300 degrees, medium temperature between 100 and 300 degrees, and low temperature for hot water, low 100 degree. So this difference is important for the technology that we can use to recover the heat for district heating. So for high and medium temperature, we consider heat exchanger. For low temperature, we use heat exchanger plus heat pump to extract waste heat for district heating. At the end, for calculate the waste heat recovery in district heating, we consider for each industrial a zone around the industrial with a configurable radius, and the algorithm will minimize the distribution cost by identifying the most densely populated census area and select route for transmission network following the existing road lines. So while using all the available waste heat is desirable to recover the investment cost of heat recovery, it could be necessary to high investment cost for transmission and distribution of the heat. So for this reason, an optimization software is needed to obtain an heat costs lower than those of the individual boiler solution. The cost that we have considered are transmission network cost, that means installation, that means CAPEX, OPEX, and maintenance, even for the distribution cost. The cost of the heat, that means the cost that we have to pay to the supplier. Investment, operation, maintenance cost of the technology that we use to recover the heat. That means heat exchanger or heat pump for a low temperature. And then we have considered even a thermal storage. The combination of heat pump and thermal storage also enables the provision of flexibility service to the electricity grid. So it's a good thing. In this, this is an example of the pop-up panel that appears when selecting one of the points represented the individual site. The map shows the transmission line in red and the census area where it is distributed in blue. The panel displays the considered radius, the length, and the cost of transport and distribution networks, the cost of investment, the capex of of the technology for recovery waste heat for high and low temperature, the energy served by district heating, and the levelized cost. In this case is 62, and the levelized cost that we have considered for a boiler, for a domestic boiler, is 120 euros megawatt hour per hour. At the end, this is the panel where a user can define the parameter. The user have to put the name and the mail, because the result of the optimization tool will be sent by email. And we have decide to have this feature because we wanted to provide to the industrial operator the possibility to input a more realistic value of their waste heat, because the waste heat that we have calculated is based on a theoretical coefficient. And so a user can put the quantity of waste heat that he really have, the equivalent hours of operation, and the costs of waste heat. That means the cost of technology and the cost of the heat. And then it's possible to change the cost of gas and electricity. This is an option to make optimization with other scenarios. Okay, thank you very much for your attention. This is the web, the address of our atlas.
Excellent. Thank you so much for that, Ada. I'm sure Luciano will agree with me with your atlas. Having 3 Italys in the world would be a much better solution for all of us. I will come back to your questions, though, at the end. It is my pleasure now to say thank you, Ada, and to introduce Juha Niemi. Niemi has a special place for us in our presentation today, because the project for which he's talking about was actually our special prize winner in the Net Zero Industries Awards this year. There have been 2 other presenters who are associated with awards. The AHEAD program and Calix was a winner last year, who of course are a partner organisation to Lilac. But it is my pleasure to introduce Juha Niemi. He's over a decade of international experience selling complex, capital-intensive industrial solutions. He has a degree in energy technology and a strong understanding of both engineering and business. Juha bridges technical feasibility with commercial value, guiding his customers through long sales cycles and enduring reliable outcomes. The project that he's going to be talking to us about today is industrial decarbonisation with the sand battery. So please, Juha, over to you.
Thank you, Alan. Thank you for inviting us, Polar Energy, to this webinar. Yeah, Polar Energy is a developer of a thermal energy storage system called the sand battery, and it's a partially patented technology. And with our sand battery, we are able to decarbonize the energy supply in general, but also industrial processes, and we do this on an industrial scale. So you will not be able to buy a sand battery for your own home. Polar Energy has currently 24 employees, mostly engineers and PhD graduates. And our sand battery is on a high technical readiness level, so TRL of 9. So we can deploy the system on an industrial scale to our customers. And we have built so far 5 sand batteries. 2 of them are commercial projects. and we have gathered so far roughly 9 million euros of funding. And the company got founded 2018 by two power plant technology engineers. What are the main benefits of the sand battery? So first and foremost, we can save thousands of tons of greenhouse gas emissions. And in addition to that, we can of course also support our customers and the region where this is applied in the expansion of renewable production. Then second, we have a low capex price per kilowatt hour per storage capacity, which is in a range of 10 to 40 euros per kilowatt hour. And in addition to that, we can reach low OPEX costs and also thus low levelized cost of heat. Then it's a long time investment. We designed a system for 30 plus years, and we can do that since we have very little moving parts. Actually, we have basically only one moving part in the whole system. And it's a sustainable technology. We don't use any toxic or harmful substances. Basically, the sand battery is built out of sanded steel. Why do we need such technology? So here we have some data which shows the increase of renewable production, which is of course intermittent production, and we need storages to cope with that production, and that gives us also two advantages. So the first one is price arbitrage, so we can use the volatility in the price, and also we can use other markets like balancing markets, imbalance markets, and curtailment markets. And the other part is that we can support the grid to be stable and reliable and more resilient. This is a simplified illustration of the sand battery, how it works. So we have our supply from renewables, and the sand battery consists of three main components. It's a resistor, a blower, and a heat exchanger, which are connected to each other with a closed loop piping system. And what we do is we heat up air, clean air, to 650 degrees and transfer the heat from this hot air via this piping system into the sand in this container in the tank. And on the other side, we can discharge the energy with a heat exchanger or with a steam generator for an industrial process. So we have only one moving part, which is the blower, and everything else is basically static. And we can scale the capacity up to 1,000 megawatt hours, so 1 gigawatt hour of one charge. And we can reach a very high efficiency, a round trip efficiency of 90%, and this is due to the storage media, so sand, which is solid. And the reason for the high efficiency is that we can manage the temperature gradient in the storage, or the distribution of the heat in the storage. So we can keep the outer layers cooler than the core, and the outer layers act already as an insulator. So that gives us an advantage in the efficiency. Basically, we supply heat with our sand battery, and we can supply this heat in different forms. So we can produce hot water, other hot liquids, We can produce steam for industrial processes, or we can produce hot air for drying process, for instance. And in the future, we gonna transfer the heat back to electricity. So this is an ongoing development in our house. And the sand battery can be applied to different applications, heat users, so not only energy supply, but also in different industries, food and beverage, chemicals, and so forth. So basically, we only supply heat, and the heat can be used where it's needed. And with the sand battery, we can decarbonize the production and the use of heat, and we can save thousands of tons of greenhouse gas emissions over the lifespan of one sand battery, and we can cover a vast amount of industrial heat use with this solution. Here you see some pictures of projects we have delivered or are ongoing. We have built a pilot in 2019 for basically for our own use and research. Then in the middle you see two commercial projects delivered so far. The first one in 2022. It has been now in operation since 3 years, and then the first industrial scale sand battery in the third column with a thermal and electric power of 1 megawatt and 100 megawatt hours of storage capacity. And we have this ongoing development where we transfer the heat of sand battery back to power, so sand to power, which allows us then basically to replace CHP operations. And this is a close-up view of our first industrial scale sand battery, which has been commissioned in June this year and handed over to the customer, and it has been covering the heat demand at a community with district heating since then. And today we are able to announce a new project where we scale this technology up to 250 megawatt hours of storage capacity. This has just been announced today. This was my presentation. Thank you very much for your attention.
Excellent. Thank you so much, Johan. We actually have our next Q&A session starting now. So again, please throw your questions into the chat or the Q&A field to do it. But I do have a few questions to start with. To give everyone else time to turn their cameras back on, Johan, I'll ask you a question first. And it's been about 6 months since you built that largest plant there in June. How has it been performing? What kind of performance have you been seeing from it at that scale?
Very well. So the customer is very satisfied with the performance and the results, and we have even exceeded the guaranteed efficiency targets, and the customer has given us the feedback that it's basically the easiest thermal system they have with which they operate. So it's a very easy system to operate.
Excellent. And you mentioned obviously with the announcement today of the 250 megawatt system, but where to? What are the plans for the future? How big could you go? How wide could the technology be applied? How easily can it be adopted by new customers?
It can be adopted very easy and easily, and we are looking for projects now, next projects for up to 10 megawatts and 1,000 megawatt hours of storage capacity, and we are looking to expand into the European markets, going to the Baltics and Central Europe as a next step. And then, of course, we built this sand to power pilot plant for the transfer of the heat back to power.
Excellent. Well, that indeed will be an exciting application to put into practice. For my next question, it's for Ada. Ada, if you can come back on, please. And I applaud the Waste Heat Recovery Atlas in terms of its intent, but who specifically are you targeting as the audience? Who are the main customers that you're looking to address with your Waste Heat Recovery Atlas?
Okay. This atlas is intended both for district heating operator to assess a first evaluation for the cost of the heat recovery building of the intervent, and to evaluate the zone that can be involved in the heat distribution, but is even interested for administrator that can evaluate possible incentives or identify the best area to intervene for this heat recovery.
Excellent. Thank you, Ada. To help the audience a little bit, is the total amount of energy that you believe can be recovered in Italy?
We have evaluated that we have more or less 30 terawatt hour of waste heat. Of these, we can use for district heating 18 terawatts per hour, and by our algorithm we have 15 terawatts to the user, direct to the user, due to the thermal losses.
That's incredible. Thank you for that.
Okay.
Please, no, if you'd like to add.
No, that means more or less we have a coefficient of between 25 to 5% of primary energy that is can consider like waste heat.
Excellent. In fact, that was going to be my next question, putting that into scale, 5 to 25%. That is incredible. Thank you for that answer. The next question I have here is for Emma. So just jumping back to that first topic that we had in our second panel, what are the main barriers remaining for full industrial electrification in your view?
Thanks for the question. And I think it differs depending on the country, but we work on at a global level. And while there are technology issues, we can see that we can overcome those technology issues, or we are working towards that in some areas. But really, for a lot of countries, the problem is the cost of finance and how to finance the change to electrification, because it is a big cost to them, and the cost of finance varies widely across the world. So in some of our emerging economies, they pay a lot more for the product, and their paybacks can be very big. We also have issues to do with the spark ratio, the difference in cost between electricity and gas. And that means that companies can be slow to change to electrification. And we saw that, I think, when we looked at what happened after the Ukraine crisis. We tried to do a push towards efficiency and to electrification, but often people went back towards gas then when the price difference changed again, and they were worried about that spark gas. And then I think the other things that we have are things to do with security of supply and reliability of the electricity system, actually getting a connection onto the electricity network, increasing your connection for the individual facilities, and continually grids. Grids are a huge issue to do with electrification, and without the sufficient grid structure, there won't be enough rollout of electrification. So they are the barriers, but there are lots of opportunities as well. So yeah, barriers to be overcome.
Excellent, thank you. So another question that I have here for you is, how, in your view, how can electrification support competitiveness goals?
Electrification is key in our competitiveness goals, and competitiveness is one of the areas where we're finding huge traction with our member countries at the moment. And while people have different reasons for investing in energy and energy efficiency, increasing the competitiveness of our industry is one of the key drivers for government to be investing in the energy efficiency and in the energy networks at the moment. So again, it's through increased security of supply that boosts our competitiveness, increasing our efficiency. Obviously, in the first slide that I showed, there's a huge increase in efficiency that can be achieved through electrification. There's obviously the safety issues and the multiple benefits. And I think globally, again, when we look at maybe especially our emerging economies, there's an opportunity for our emerging economies to leapfrog forward in terms of the technology that they use and the access to technology that they have. And this is especially important in some countries where they do not have access to gas infrastructure or to fossil fuel infrastructure, but they do have access to solar voltaic or PV, where they can generate their own electricity, especially with storage facilities as well. It means that they can increase production, or they can diversify production, or the production can take place where the raw material is made. And that can be a huge gain in terms of the just transition in our energy system. And that can only be achieved through electrification and through efficient electrification. So yeah, there's huge gains for competitiveness throughout the world.
And an excellent point made there. Thank you so much for that answer. The next question I have here is from Luciano, and it's not a Dorothy Dixon, but it's a question for Juha on the sand batteries. Luciano has pointed out that the batteries appear to be rather bulky, and he's asking whether there's any advantages or an intention to actually install them underground with the opportunity to save space. I'd also probably caveat that question, does it provide any disadvantages in terms of trying to put the facility underground? So Juha, would you like to answer that one for us, please?
Yeah, thank you for the question. So technically it's possible to build it underground, and there will in the future definitely come across sites where we have to think of that solution. I think there is one. It's not a bit disadvantage, but there's let's say a slight risk that the sand shouldn't get wet, so it should stay dry. And if you put it on the ground, there's a risk. But yeah, with proper engineering, it can be omitted, of course.
When you mention risk, we should probably mention that are we talking about explosive steam generation, or?
No, it's just not efficient anymore. So yeah,
good.
Of course it will generate steam, but it's not let's say it's not a tight construction,
not a pressure vessel.
No, it's not a pressure vessel. Yeah.
Good to let people know that, so that they're not worried about that risk. Now, everyone, that is the full list of questions that I have. Unless there is a very quick one coming in, what I'm going to do now is to hand over to Urban Piker, the Director of the Net Zero Industries Mission, just to give a quick wrap up, and to Luciano to actually give their thanks to all of our speakers and for all of our attendees today.
Thanks a lot, Alan. Shall I go ahead, or Luciano, you want to go first? I go ahead. Yes. So thanks for the opportunity to close today's webinar. I have really been enjoying the presentations, questions, and the discussions. And thank you, Alan, for moderating today's webinar again in such a nice way. Let me offer a very brief personal wrap-up of this inspiring session. First of all, it's very promising to see the level of cooperation in the area of electrification, both on the level of international organizations, but as well on the level of companies and research organizations. This is really promising, and the recent technological advancement in high temperature heat pumps has significantly enlarged the scope of use cases for electrification of industrial processes. And this has a huge multiplication potential, and as we have seen today, very much so as well in the hard to abate sectors. This is a key element in terms of increasing the system flexibility of providing grid stabilization services, and thus this is key to increase the integration potential of renewable energy sources. And if we add storage to the equation, this certainly amplifies the benefits of electrification. As always, an efficiency first principle is both a prerequisite for electrification, but it has a whole lot of other positive externalities ranging from increased competitiveness to lower overall environmental impacts. This is my very brief wrap up, and I would really like to express my sincere thanks to all the speakers for their outstanding contributions, for the projects you have been sharing, for sharing your knowledge, and for your inspiring insights. I hope that today's session has once again sparked new ideas on how to tap the immense potential of electrification of industrial processes. Reaching net zero is complex, and there's certainly a lot to do ahead of us, but solutions are there, and net zero is within reach. By that, I would like to thank you once again. Thank you, Luciano, for co-hosting this. It's been a pleasure. Thanks for your support, and we look forward to continuing this important journey with all of you. Thanks.
Thank you very much, Urban. I totally agree with you. I think I would like also to join you in thanking all the speakers for sharing and showcasing their important, interesting project, and also the knowledge they gain in their activity. I think this is the main essence of the webinar. I thanks also the people attending the webinar and making interesting questions. And also I join you in thanking Alan for excellently moderating the discussion and making the webinar more live. Thank you. I think this is just the first attempt. The importance of electrification of the industry is so important for everyone, for the clean energy transition. In our case, we deal with the power to X, power to hydrogen, power to heat. So I think there is some good ground for future collaboration with your mission. I think this is part of the story of Mission Innovation being an international platform where communication is live, where knowledge sharing is possible and very much needed. I think the interesting presentation gives us also some very good hope for the future, finding different solutions for different applications. And I think hard to abate sector really deserve this type of solution. As you said, system flexibility is key. And when you talk about system flexibility, our mission could enter into the game. So we offer our full availability to discuss with you for future webinar, future joint activity, an example of practical solution that can make a change in our life. So thank you, Alan. Thank you, Urban, for motivating us to join you for this webinar. And as I said, it was a very nice experience just to be repeated. Thank you so much to all the attendees. I was glad to be with you today. Thank you.
Thank you both. It was our absolute pleasure. Again, everyone, this brings our webinar today to a close. It will not be the last in our series, so please,